All right, good morning, chemists. We'll get started now. So the plan is to finish up chapter 16 with some randomized practice questions to see if you really got it. Understanding the strategies here, what are we looking at? An acid, a base, the conjugate of an acid, so therefore a base, or the conjugate of a base, an acid. How are we utilizing the ice table? Is it, are we calculating the equilibrium line and calculating or making an approximation, or are we given other information to fill in our ice table so we can approach the problem? So that's the kind of things you want to be asking yourselves as we go through the remainder of this chapter and the next chapter, really. Are we working with an acid or a base? What K expression is most appropriate to use? What is X when we calculate the ice table? Is it either H plus or is it hydroxide concentration? All these things matter, and we should be asking ourselves these questions. And then finally, is our calculated pH consistent with what we predict? So this is a calculators out kind of day. So go ahead and do that. So just a reminder, all right, are we working with an acid or a base? We utilize the ice table two different ways. Method one, which I affectionately call the Sudoku method, where we are given a piece of information that allows us to fill in the entire ice table, and then typically we can calculate Ka that way. Versus method two, this requires the quadratic, or like 99% of the time we use an approximation where we're given Ka, but we want to calculate pH, so the equilibrium line. So I have an assortment of questions for us to attack, and so let's see if we can conquer these. All right, so always be asking yourselves, acid or base? What K should I use? And then finally, what kind of method am I using the ice table? So this first question, what is the pH of a 0.1 molarity HF solution at this temperature? So what is HF? It's an acid, yeah. So what K should I use? Ka. Am I given Ka? Yes, perfect. So I just go ahead and use that Ka value. But I'm going to do the full ice table anyway, so we can remind ourselves how this works. Right, Ka, A stands for acid, so HF acting as an acid, pops off, donates an H plus, leaves an F minus. We put our ice in here, 0.1 molarity HF, that's the concentration on the bottle. That is the initial concentration of HF. We have 0 of the other stuff. Which way does this reaction have to go? Forward, so it's minus X, plus X, plus X. So at equilibrium, we lose a little bit of our original HF. It ionizes into H plus and F minus. What is the trick with ice tables? The E line goes where? Into the K expression, as always. And so we stick that E line into our Ka expression, which we know is products over reactants, so H plus, F minus over HA. And so plugging in those actual numbers, we get X squared over 0.1 minus X equals Ka, and that's given, 7.2 times 10 to the negative 4. All right, so if we solve, is this easy to solve as written right now? No, that requires the quadratic. Do you want to do the quadratic? No, so what should we do? Yeah, let's neglect that negative X minus X. Here's the reason we can do it. So let me just solve for this. So when you solve for this, you get X equals, I wrote it down somewhere. I wrote it down. 0.0085 molarity. Okay, now so that X we just calculated. In your calculator, do 0.1 minus this number. Does this 0.1, does the denominator value change that much? It doesn't. This number that we're subtracting from 0.1 is really small, so it has very, very little effect of our final answer here. And so that is why we are allowed to neglect X, because this is going to be a small value. And additionally, the small value that we're subtracting is being subtracted from a large value. So that large value is not going to change. And that's why we can make this approximation. When the minus X is small, but the thing that we're adding or subtracting from is really big, it's not going to change that much. It's like giving Jeff Bezos $1. or taking $1 from him. He gets poorer technically, but like, does his whole net worth change that much? No, it doesn't. All right. I know I use that analogy a lot, but it works. And that's why we can make the approximation. So we calculated X. How is X related to our answer? X is concentration of what? H plus, yes. How do we know that? Either from the ice table or understand you used Ka. Ka always has H plus as a product. So then to get the pH, we just negative log that number, and then yeah, we get a pH of 2.09, right? So 2.09, that is acidic. Remind yourself, what did you put into the water? An acid. So does that match? Yes, perfect. So we can move on. Our brains are happy. We can move on. All right, so let's do another one. So that was a method 2, right? We had to approximate. So let's see this one. What is the pH of a solution when we add 0.1 moles of sodium fluoride into water and dissolve it in half a liter of water? So ask yourself, what am I putting into the water? An acid or a base? It's a base, yeah, because sodium fluoride contains F minus. That is the conjugate base of HF, which is an acid. It's a weak acid, right? So F minus is a base, so what K expression makes most sense to use here? KB, yes, but we got a problem, don't we? Were we given the value of KB? No, but how can we get around that? Use Ka, all right? So since Ka for HF is given, F minus is a base, so we want to use Kb. Kb is simply Kw over Ka, the value that is given. So we're assuming that this is at 25 degrees Celsius, so we know Kw. Ka is given, so you can go ahead and calculate that Kb is 1.38 times 10 to the negative 11. That is Kb. Right? And so since we're using the Kb expression, it makes most sense for us to use a Kb reaction, a Kb ice table. Bases, always a little bit trickier, all right? I feel like acids, it's easy to see like, oh, you got HA, H pops off, and A minus is left over. They like separate, they ionize. But bases are a little bit weirder, where for a Kb expression, you have to have a water molecule there. In order for F minus to act like a base, it needs something to steal a proton from, so water has to be there. You do the equilibrium, F minus steals that proton back to make HF, and then you're left with hydroxide, since this is a Kb expression. So we do our ice table, nice and good there. All right, and so similar setup. Do I put 0.1 under F minus? No, I don't. Why? But it's 0.1, just like the other one. Yes, that's moles. What is the unit of an ice table? Molarity. Ka, Kbs, those are all concentrations. Kps are atmospheres or pressure, but that's okay. Here, Ka, Kbs have to be concentration. So it is not 0.1. It is actually 0.2 molarity. Yes, because we're dissolving it in half a liter of water. All right, so do recognize that I could change up the question like that. All right, I have to have some random amount of water. It doesn't matter how much, and then 0 amounts of everything else. So this is really no different than the Ka expression, except water is there. But in the end, water does not end up in the Kb expression, but it still needs to be there to be balanced. So this reaction must proceed in which direction? Forward. So minus x on water, plus x. So at equilibrium, we have 0.2 minus x of F minus, x of HF, x of hydroxide. Again, I don't care how much water I have because it's not in the K expression. So the E line goes into Kb. It ends up being x squared over 0.2 minus x equals that Kb we just solved for, but again, Kb is Kw over Ka. It is equal to 1.38 times 10 to the negative 11. All right. Is it simple to solve this as is? Nope. So what should we do? Approximate. Yay. Approximate, and again, we can say that because 0.2 is a rather big number. X is going to be a small number. So this reduces down to x squared over the initial concentration of that F minus. equals KB, 1.38 times 10 to the negative 11. You get that X is equal to 1.67 times 10 to the negative 6 molarity, but it's the concentration of what? Hydroxide this time, because that's what the ice table says. Also, this is a KB expression, so there we go. There is X, but now let's actually get the pH. So when I negative log that number, I'm calculating what? pOH. So the answer I get is actually 5.78. All right, and so our pH is 14 minus that. Again, we're assuming we're at 25 degrees Celsius. So 8.28 is our pH. That pH is what? Basic. What'd you put in water? A base, perfect. Because if you stopped at 5.78, I hope that you would catch yourself. 5.78, oh, that's acidic. But it's not, we didn't put an acid in water, we put a base, all right? So hopefully you can catch things like that. Again, let me emphasize the meaning of this approximation. We do the approximation so we don't have to do the quadratic. We just, with the approximation, got that X is times 10 to the negative 6. If you put that number back into the unapproximated form, does the value of the denominator change? It does not. You're subtracting such a tiny number that the value of that denominator does not change. So when we shouldn't approximate is when you do the minus or plus X and the value does change. That means we can't do an approximation. Again, we can approximate because X is small and the value we're subtracting it from is also small. Okay, keep going. So that was another method too, use an approximation. Usually if you calculate pH, you have to do that. Okay, let's do another one. Okay, 0.04 molarity of an acid is 2.2% ionized. Calculate all of the equilibrium concentrations and Ka. So this one's a little bit different, but it's an acid. So what expression should we use? Ka, and that's exactly what we're solving for. So I'm just going to use a generic acid. I'm just going to say HA. Decomposes to H plus and A minus. So I'll fill in my ice table and figure out how I'm going to approach this. So here is the concentration on the bottle, 0.04 molarity. All right, so this reaction must proceed in the forward direction just like the rest of them. So at equilibrium, I have 0.04 minus X of the intact HA, weak acid, X amount of H plus, and X amount of A minus. So in this question, I want to calculate equilibrium concentrations of everything and Ka. So this question's a little bit different because there's a piece of information we haven't used yet that's going to give us a hint at that equilibrium line, and that is that 2.2% ionized. We got to remember what that means, all right? So percent ionization is equal to, and this is an equation that's given to you on the exam. I'm trying to think, was it given to you? No, it wasn't given to you in the last midterm because we didn't do weak acids, but it is for this midterm, for midterm 3, because we are covering weak acids. So percent ionization, what this percentage is how much of your reaction proceeds forward. How much X do you produce relative to how much you started with? That's the idea of percent ionization. How much H plus, how much product are you losing from your initial reactant? So percent ionization is H plus concentration at equilibrium. Usually this is equal to X in your ice table. So if this was a base, it would be hydroxide concentration over how much weak acid you started with initially. That's percent ionization. How much of your weak acid did you lose? That's the big idea there. So since we are given percent ionization, it's given that it is 0.2 or 2.2%, so 0.02, equals H plus concentration at equilibrium. I'm trying to calculate that. I actually already know the initial concentration on the bottle. That is 0.04 molarity. So that 2.2 ionization means 2.2% of that 0.04 molarity gets ionized into H+. And so we're going to calculate, okay, how much H+ is actually produced at equilibrium. And that's going to be our X value. So H+ at equilibrium, which is also equal to X, equals something like 0.00088 molarity. Right? So there's X. You could calculate the pH as well here if you wanted to. Yeah, you could convert percent ionization to pH. We could also solve this question if I gave you a pH instead. Right? So that is X. So we already answered half of the question. We now know the equilibrium concentrations of H+ and the conjugate base because both of those are equal to X. So we have these two values. Now the concentration of HA is how much we started with initially. So we're going to plug that X back in. So HA at equilibrium is 0.04 molarity minus that X we just calculated, so 88 molarity. So at equilibrium, we're just going to have a little less amount of that intact acid. So what is this? Where is it on here? 0.03912. All right, so just a little bit less. All right, so there are all our equilibrium concentrations. There is X, H+, and A-, and there is the equilibrium concentration of the intact weak acid. So now we can calculate Ka because those Ka values are always equilibrium concentrations. All right, so it is H+ at equilibrium, A- at equilibrium over HA at equilibrium. To show the full work, I'll just put in the ice table variables anyway. So X squared over 0.04 minus X. And so, we could put those the X values in again and just solve for it, but I have those equilibrium concentrations there as well. And so the idea is this is no different than what we did in the previous two questions, but with the information given with percent ionization, this is how we get X. This is the hint to the ice table. All right, if I gave you pH, it's another way to answer the same question. pH gives us a hint as to what X is in our ice table to allow you to calculate the Ka value. So to actually solve this question now, we're going to take X squared, so the concentrations of all those things, squared over 0.03912, which we got is the equilibrium concentration of HA, and the answer is somewhere at the bottom, right there. 2 times 10 to the negative 5, right? So this question is different. Should I make an approximation here? No, why? You know what X is. So if you make an approximation and you just say, oh, the denominator is 0.04, you are just being lazy. You know what X is, just plug it in, right? The point of doing an approximation is to avoid using the quadratic. There's no quadratic here. You know what X is, just plug it all in and do the algebra. All right, so again, you could solve this question the exact same way if I gave you pH instead of percent ionization. Both of those things give you X to then plug into the Ka expression. All right, let's do one more. Kind of like this one. Here we have a solution of acetic acid with this pH. What is the molarity written on the bottle? And there's the Ka value. So you just have like an unknown stock solution of acetic acid in lab. You put in your pH probe, and that is enough information for you to figure out what the concentration should be written on the bottle. So let's approach this question. So HA is an acid, so we should use Ka. And look, we're even given Ka. Fabulous. So let's just write a generic Ka expression. So HA becomes H+, A-. Do my ice table stuff. So in the previous question, we wanted to calculate Ka. In this question, I give you Ka, and I'm actually looking for a different spot on this ice table. We want to know what is the molarity written on the bottle. So what term do you think that is in this ICE table? It's the initial line, yeah. So we need to figure out what this number is, whatever goes there. Because like in all of the other 3 questions we did, we were always given the initial concentration. So we're just working backwards. Let's take all this information and figure out what that initial concentration is. So I'm just going to make up a number. I'm going to say we start with N amount of HA. 0 of that. Hopefully this all looks familiar. This reaction has to go forward. So at equilibrium, we have N minus X of HA. X of H plus, X of A minus. All right? So we need to figure out what this N is. So let's just go ahead and plug that into the Ka expression because I give you what that is. So Ka is X squared over N minus X equals 1.8 times 10 to the negative 5. Can we solve this as is right now? No, there are 2 variables. So we haven't used pH yet. What piece of information, which variable can pH tell us? X, yes, because X is equal to H plus concentration at equilibrium. So this is equal to 10 to the negative pH of the solution, so 10 to the negative 3.45. So we get that X is equal to 3.55 times 10 to the negative 4. All right, so we can plug that X value back in to the Ka expression and solve for what N needs to be for all of this to be true. So I'll just pick a different color here. So 3.55 times 10 to the negative 4. That whole thing is squared. Again, this is my X value. Over N minus, should I approximate? No, never. Because we know what X is, 3.55 times 10. The reason I say is because I see people approximate all the time. They just keep taking away the minus X. But in this case, we know what X is, so no need to approximate. And I will die on this hill. So N minus that equals 1.8 times 10 to the negative 5. There is one variable. We can easily solve that. So I'm going to move some stuff around. I'm going to bring that one over here and that one over there. So I didn't do the math here. Okay, so 3.5 E negative 4 squared divided by 1.8 E negative 5. So that side of the equation I'm moving over here is 0.0068 equals N minus 3.55 times 10 to the negative 4. And then so add that 3.55 to both sides. So plus 3.55 E negative 4. Oh wait, I messed up. That plus 3.55 E negative 4. Boom. Yes. All right. So I get, oh, my number's a little bit off. Where did I probably put some number in wrong. I got N equals 0.00716 molarity. Mine's a little bit different. Probably one of my numbers went off somewhere. And so that would be our initial concentration on the bottle. So in this example, pH gave us X. We are actually solving for N, and we can do that because we are given a Ka value, right? So just a different variable. All right, so in this case, this is like a type 1 ICE table where I give you X. No approximation is needed there. All right, so in all of these questions, you know, the first part of the strategy is, what am I dealing with? An acid, a base, because that will guide us on what kind of K expression to use. So the last part of this chapter is just to summarize pH calculations. So how we calculate the pH depends on what we're putting in the water. So there's 6 different scenarios, right? So being able to look at the species you're dissolving in water, recognizing which of the 6 species am I working with will guide us on how to calculate the pH or pOH for that solution. So this was from midterm 2, so strong acids and strong bases. Here, we make the assumption, if you put a strong acid in solution, you are assuming that that strong acid is what contributes the H plus concentration at equilibrium. So you can simply just do pH equals negative log, HCl, and that's fine, right? For a strong acid. You can do the same thing for a strong base, you just have to calculate pOH first. So same exact idea there. So pOH is negative log of the sodium hydroxide concentration, because we're making the assumption all of the hydroxide is what's contributing to that pOH. And then you're just one step away from pH, right? A little bit different for a base like calcium hydroxide. What's the difference there? There's 2 hydroxides for each of those. So you have to multiply that concentration by 2 before you calculate pOH. Because again, 2 hydroxides are donated for every 1 calcium hydroxide. Right, so small detail, and that's only for strong bases. There's no examples of that for strong acids. All strong acids, only the first proton is strong. Right, those are the easy ones. Those are the ones that were assessed on midterm 2. Midterm 3 is going to be a toughie because there are 4 different examples, and then we're going to add buffers to it next chapter. Recognize, okay, if I put HClO2 into water, is that one of our strong acids? So this is what? Chlorous acid? Chlorous acid? That is not a strong acid. It's only chloric, so O3 and O4, perchloric acid. Those are the only 2 strong acids within the chlorine group. So this is a weak acid. So like all weak acids, HA, what K do you use? Ka. If I'm asking you to calculate the pH, will I give you the Ka for this acid? I probably will. Yes. So that's something you can easily look up. So take the Ka that's given. When you do the ice table, what is it going to approximate to? Hopefully you can do it without doing the ice table now. Ka is going to be equal to x squared over your initial HA concentration. That's with your approximation, all right? So that's after you do your ice table. X is equal to what? H plus, and then you can go ahead and pH, and that's fine and dandy. All right, so that's a weak acid like chlorous acid, nitrous acid, those things. Or we could have like a charge neutral base like ammonia, or this is methylamine, right? So I'm just going to call it B, base. All right, so if I give you a base like methylamine here, what K do we want to use? KB. Will I give you the KB of methylamine? Yes, I will. So if we use KB and we do the ice table, what is it, the ice table going to reduce down to? X squared over initial concentration of B, just like the other one, right? I give you KB. But in this example, X is equal to what? OH minus concentration. So you have to do POH, then pH, but no big deal. Right, so that is HA and B, the weak acid and base. Well, what if I give you the conjugate? All right, so for example, this is chlorous acid. This is chlorite, sodium chlorite. Or you could think, HF, hydrofluoric acid, F minus is its conjugate base. So chlorite is chlorous acid's anion that's present. So that's its conjugate base. So A minus is the conjugate base. So what is the most appropriate K to use? K, B, because it's a base. Will I give you the KB of chlorite? Heck no. But what will I give you? Ka. So KB is Kw over Ka. Great. So that's the value you use. So Kb is equal to x squared over initial concentration of A minus. That will be given. X is equal to hydroxide concentration because we used a Kb. And then you're just a POH, pH away. I hope we're seeing this. These are the conjugates. These ones are harder. They're harder to identify because one, it's tricky to just identify, oh, this is the conjugate of something else, right? Okay, so methylamine is here. What is this? That's its, You don't even have to know its name. You don't have to know its name. You just need to know it's its conjugate acid. It's the same base with an extra proton on it. I know there's an extra proton on it because there's a chloride present here. So here is Cl minus. This is just like a bunch of stuff with an extra proton on the side. All right, so it's the salt version. So here is a conjugate acid. So if this is an acid, and here's the generic term, we want to use Ka. But am I going to give you the Ka of methyl ammonium? Nope. So you have to calculate it using Kw. So Kw over Kb. I will give you Kb. So go ahead and use the Ka expression. Ka x squared over initial concentration of the conjugate acid, Hb plus. X is equal to concentration of what? H plus, yes, because it's Ka, and then UpH. That is every pH calculation just summarized in one place. You need to ask yourself, am I working with a strong system? Am I working with a weak system where the Ka is given, or am I working with the salt of a weak acid, weak base system? All right, so let's practice it. I'm going to give you a bunch of stuff, and I don't want you to actually calculate these. I just want you to set it up correctly. Set it up correctly. I have the answers down here if you want, but let's work through these and see if we can't just set them up correctly, because all of them are going to follow the same form, right? They're all going to be x squared over initial concentration 0.1 equal to something. We need to figure out what that something is. So here's the information. All of this is method 2, okay? So it's x squared over something, make the approximation. Okay, I'm going to give you 2 Kas. This is all the information. So this is for hypochlorous acid and benzoic acid. Those are 2 Kas. And then here are 2 Kbs. This is for ammonia, and this is trimethylamine, so 2 Kbs. We have all the information we need to solve the pH for all of these. So 0.1 molarity HClO. What is HClO? An acid, a weak acid. So we should use what K? Ka. Am I given that? Yes. So perfect. So this is going to be x squared over 0.1 equals Ka. X is equal to what? H plus. So then you go ahead and pH. Boom, you're done. Okay, we are given Ka. That's why I can use that. We're given Ka for hypochlorous acid. Okay, what about the next one? 0.1 molarity NH3. We want to use what? Kb. Am I given Kb? Yes, so I can just go ahead and do x squared over 0.1 equals Kb because we're given that Kb. But this one's different. X is equal to OH. So we have to POH, then pH. Perfect. All right, next one. NaClO. What's that? That's a base. Yes, that is the conjugate base of the acid. All right, so this is ClO minus. So what am I going to use here, Ka or Kb? Kb, but did I give you Kb of that? Nope. But we can solve for it. So it's still going to be x squared over 0.1. I hope that you're recognizing the trends. But we're not given Kb, but we can solve it using Kw. Kb is Kw over Ka. We do know what Ka is for HClO. Perfect. X is what? H plus. So, no, it's not. It's OH minus because we used Kb. We used Kb. And so, yeah, you POH, pH, whatever. Next one, what the heck is that? That is ammonium. That is a weak acid. So we have to use Ka. Did I give you Ka? No, but we can calculate it. Ka is equal to Kw over Kb. I did give you the Kb of ammonia. You seeing it come together? And if you want, you can calculate these. I have the answers on the next slide, just so you make sure you know what you're doing. All right, X is equal to what? H plus, yes. Look, we're doing all of this without an ice table. All of these actually technically require an ice table, but they all follow the same form. I just want you to have the skills to be able to identify which K to use, because you can do the ice table, right? And you can still screw up on which K to use, and you'll get the answer wrong anyway. So the important thing is knowing which K to use. All right, and then you pH directly. All right, next one. 0.1 molarity HClO4 is what? It's a strong acid. See, I tried to trick you, right? Because I technically, will you ever find a K for a strong acid? Nope. So how do we find the pH? Just negative log it. Yeah, so this one is a strong acid. I tried to trick you, but you are good. This is negative log 0.1. So I think the pH is 1, something like that. Yeah, so do be on the lookout for that. Okay, next one. What is that? Squint your eyes. Squint your eyes. Doesn't that look really similar to ammonia? It's really similar. Just take each of the H's and replace it with a CH3. All right? So this is a what? Base. So we're going to use Kb. Did I give you Kb? Yes. So it's x squared over stuff. X is equal to hydroxide concentration. Go ahead and do POH and then pH, whatever. Right, next one. What the heck is that? It is an acid. Just, again, squint your eyes. All right, squint your eyes. What this salt is the base with just an extra hydrogen or proton on it. So this is really no different than NH4+. We need that nitrate there to make it charge balanced. So yes, this is a weak acid because it's the conjugate of ammonia. These ones are more difficult. They are more difficult to recognize the bases. Most students, they can get behind the, come on, my fingers, like NH3, the base, NH4+ ammonium. These examples are no different. They just differ by one hydrogen. It's just the things that are attached to ammonia are different. They're just like methyl or ethyl groups, right? So that is a weak acid. So which K do we use? A, yes, but did I give you Ka? No, so it's Kw over Kb, which is given for the base. So then it's x squared over whatever. X is equal to H plus concentration. Okay, benzoic acid is a what? Acid. So we use Ka. Did I give you Ka? Yes, I did. Look, it's right there. Perfect. So x squared over 0.1, x is equal to H plus concentration. Perfect. Go to pH. What is sodium benzoate? That is a base. So here's the thing. So like, let me think of an example. Carbonic acid, all right? Carbonic acid is a weak acid. The anion is carbonate. Yeah, do you remember your acid naming rules? Ates become ic acids. So if this is benzoic acid, its anion is benzoate. So oops, my sausage fingers. Benzoic acid is HA, that is your weak acid. Benzoate is A minus, right? Okay, so A minus is a what? Benzoate is a what? It's a base, so we use Kb, but how do we get that? Kw over Ka, where x, oh yeah, equals x squared over junk. X squared over stuff. X is equal to hydroxide concentration, UPOH, and then pH. All right, do we feel really smart? I hope so, yeah. There's a pattern. There's a pattern here. Learn the pattern. We can always make the approximation for pH calculations. That's always a type 2, ice table where we're calculating the equilibrium line. 99% of the time we do an approximation. Yeah. What if we get a negative number for the OH? You will never get it, ever. Because here's the thing. How do we solve for X? How do we solve for X? How do we solve for X? You have to calculate all this stuff, right, and take the square root. If you take the square root of a number, will you ever get a negative number? Never. That's literally, I think, a rule in math. Like you can never get a negative number there? Yeah, or plus or minus. Yeah, so it'll just always be a positive number. Concentrations are always going to be positive here, all right? So, no, you're right, it can be negative, but the negative will never be the answer here because these are concentrations. You might be thinking about POH and pH. You can get a negative POH or pH, that's fine. Okay, no, there's a big difference there. You can't have a negative concentration, but you can have a negative pH. So for example, okay, let's pretend we're at 25 degrees Celsius, and I have something that is like HCl is 0.1 molarity. What's the pH? Can you tell me? Without your calculator? Or just put in your calculator. What's the pH? You asked the question, you're solving it. What's the pH? Okay, this is a pH of 1. 1. That's the rule of negative logs, okay? So what if I have a concentration of 1 molarity instead? What's the pH? pH is? It's not 1. Take the negative log of 0. Or sorry, negative log of 1 is equal to 0. Just put it in your calculator. Put it in your calculator, okay? What if I had an HCl concentration of 10? That is negative 1, yes, negative 1. And so what would the POHs of these be? If it's all at 25 degrees Celsius, pH of the first one would be 13, the second one would be 14, and then the third one would be 15. Or wait, yeah, 15, yeah, because they always have to add up to 14. So since this pH is negative, again, pH plus POH has to equal 14. Okay, there we go. All right, so that is chapter 16. So what does that mean about homework? It is due on Monday, yes. So we're going to move on to all the weird things in chapter 17. Okay, so we are still talking about acids and bases for the most part. We're still talking about aqueous equilibria. So you need to constantly be asking yourself, should I be using Ka or Kb? What do the magnitudes of those K values mean? What does that mean about the conjugate? All those things are really important in this class, or in this chapter. I taught this at 8 a.m. and at office hours, someone was like, after today's lecture, I felt really smart because things are going to get complicated real quickly. But hopefully you'll see, oh, the math matches our intuition, which is nice. Okay, so let's move into it. Okay, so we're still talking about acids, bases, so we're going to constantly be using this pH calculation. Again, 99% of the time, we're at 25 degrees Celsius, unless I tell you otherwise and give you a different kW value. So for the most part, we're at 25 degrees Celsius, so kW is 1 times 10 to the negative 14. Okay, that's not new. What is new is the Henderson-Hasselbalch equation, where in chapter 6, for the most part, all of those pH calculations, only one thing was in solution, either a weak acid or a weak base, nothing else, and we did our ice table. The Henderson-Hasselbalch equation describes a buffer system, meaning in a solution you have both a weak acid and its conjugate base present, both in large quantities. That's what a buffer is. I affectionately call our own bodies, I say that we're big water bags, but to be more specific, we're buffer bags, okay? Where like we drink a soda is acidic. We drink it and like our pH doesn't crazily fluctuate if we drink one soda, and it's because we have these buffer systems in our bodies to accommodate large disruptions and pH changes. So we'll look at that in this chapter. All right, recall how we calculate pH. This is actually just the slide we went over. The 6 different options is, do we have a strong acid, strong base, weak acid, or weak base, or the conjugates of those things. This last column is definitely a lot trickier. And then the last idea, the last type of thing we can have in a solution is a buffer, meaning we have both a weak acid and its conjugate present, or its weak base and its conjugate present. That's what a buffer is. All right, so that's the last kind of pH that we will calculate. That is just review. We already went over that slide. Okay, so Let's talk about some weird scenarios that can happen. Again, I mentioned in like the previous chapters, for the most part, only one thing was ever in solution for us to calculate the pH. In chapter 16, I did give one example where it was like a mixture of HCl and like nitric acid. Both of those are strong acids, so both of them contribute to H plus concentration to calculate pH. You just calculate both of them, all of the H plus present. But, well, what if we're mixing acids and stuff, and let's say both of them are weak, all right? How would we calculate the pH there? So in those examples, the strongest acid in your calculation, the strongest acid in your mixture is what goes into your calculation. So for example, I have two acids right here, HCN and HNO2. Which acid is stronger? HNO2. This one's stronger because Ka is bigger. So this value we're going to use to calculate pH. We are going to ignore the other one, right? Because for both of these, don't you just do x squared over initial concentration equals K, right? When you, like if you did that for this first one, x is going to be a real small number. It's only going to contribute a little bit of H+. But this acid, the one with the bigger Ka value, its x, its H+ concentration is going to be a bigger number, and that's the one that matters here. And that's the one that's going to affect our H+ the most. So we're going to just ignore that weaker one because it's weaker. Doesn't make a lot of H+, isn't going to change the magnitude of pH, but this one is larger. All right, or no, I don't want to say larger, I want to say stronger acid. All right, okay, so we're going to just pretend all we have in solution is that nitrous acid. So how do I set up the pH calculation? X squared over 0.2 equals that Ka, 4.6 times 10 to the negative 4. X is equal to H+ concentration. You can solve that. Did I do that? Maybe. Nope, I didn't. 4.6 E negative 4 times 0.2 square root. I get X as 0.0096 molarity, so you negative log that, and I think the answer is in the corner. It's fairly acidic. It's 2.02. Very acidic. Okay. So that's a mixture of two weak acids. Pick the stronger one. That's the one that's going to dictate your pH. What if we have a mixture of HCl and acetic acid? How would you approach this pH calculation using the same ideas? HCl. Yes, we're going to use HCl. Do you have to do anything with acetic acid? Nope. Acetic acid only ionizes a little bit. It's only going to give us a little bit of H+, but HCl, on the other hand, ionizes fully. We're just going to assume that H+ in the total solution is that 0.1 molarity. Without using a calculator, take the negative log of 0.1. Tell me what it is. It is 1. Okay, if you don't know that at this point, I urge you, when I do things, actually put it in your calculator and see it. See it for yourself, because if at this point you don't know if negative log of 0.1 is 1, that's an issue. Okay, let's keep going for, again, the strongest thing wins here. So H2A is a diprotic acid. Let's pretend that we have a 0.1 molarity solution of H2A. What is the pH? Here are two Ka values. Here's the Ka1 for H2A, and then here's the Ka2 for HA minus. Which K do we want to use? Ka1 or Ka2? Ka1, yes, this is the one we want to use, not only because it's the stronger one, but that's the thing that we put into solution. We put H2A in solution, all right? The question would be different, and we'd have to solve it differently if we were talking about HA minus, but in this case, H2A is the largest thing present, so we don't have to worry about Ka2. So in this case, we're going to just ignore Ka2, and we're going to use Ka1. So 1 times 10 to the negative 3 equals x squared over 0.1, and then go ahead and solve for pH. So we're just using Ka1, not Ka2. Okay. So that's if we have a mixture of different things. It's usually the strongest thing that dictates our pH calculations. We cannot do simultaneous equilibria. That's outside the scope of this course, but if you take higher level chemistry courses, you will look into that. Well, what if you have two weak acid systems? How do they interplay with one another to get that pH? But for the most part here, we're going to assume only one substance is the important one, so it just ends up being one pH calculation. Okay, so there's a weird scenario. And this will come back. We're going to look at, as we do a titration, there's going to be a mixture of things sometimes, and that will dictate how we approach the pH calculation. Okay, this is my favorite slide in 1220. Okay, I told you this is the chapter of weird stuff. I feel like I've taught you well, and you'll understand this. Okay, so what is the pH? Hopefully you can do this without a calculator. What is the pH of a solution that is HCl is 1 times 10 to the negative 3? What is it? pH is what? Is what? 3. I mean, put it in your calculator. Please, if you don't know that it's 3, put negative log times 1e negative 3 in your calculator and tell me what you get. You get 3. All right? So I hope what you see here, it's the exponent that's on the 10 tells us what the pH is. Because it's 1 times, there's going to be no decimal places. Okay, so this is a pH of 3. So tell me, is this solution with a pH of 3 acidic or basic? Acidic. Does that match your intuition? Yes, you put an acid in solution, it should be acidic. All right, what is the solution where HCl is 1 times 10 to the negative 8? What do you get? pH is equal to what? Is what? 8. Okay, perfect. Is this solution acidic or basic? Does that match your intuition? What's wrong? What'd you put in water? An acid, and you got a basic pH. Are you fine with that? Are you going to move on? No, something's wrong, right? Yeah, something's real wrong. And it's because it is wrong, right? So here's another weird example. Really, really dilute acids or bases. Strong acids or strong bases, you actually have to approach the pH a little bit differently to get a pH that makes sense. This pH does not make sense. If you become a doctor, all right, and you make a solution that is 1 times 10 to the negative 8 molarity HCl, and you tell someone that it's basic, I'm going to be very disappointed. You put in acid in water, what should the pH be? Acidic. So let's do it the right way and get a pH that is acidic. Okay, so this is why this one doesn't work, right? So the big difference between these two questions, 10 to the negative 3, 10 to the negative 8, all right? That this concentration is very large. It's a very large concentration versus when HCl is really dilute, this is a very small concentration, right? That HCl is only contributing a little bit of H+. So in chapter 16, we actually made an assumption all along. When we put a strong acid in a solution, and I did mention this in my words, but you probably just ignored what I was saying. We assumed that the strong acid was the total H+ concentration at equilibrium. We made that assumption. There's actually another source of H+ that we've been ignoring all this time. In a solution of HCl, an aqueous solution, something else contributes H+, and what is it? It's water. Water also contributes H+, yes. So water, so if you think about pure water, like pure water, and you solve for this, what is the concentration of H+ and OH- of like a pure water sample? 1 times 10 to the negative 7, yeah. So the idea here is once your concentrations of acid, added strong acid, is close to times 10 to the negative 7, we can no longer make the assumption where H+ at equilibrium is just HCl. It's when both of these numbers are similar to one another, we can't make that assumption anymore, and we have to consider water's contribution to the pH, and then hopefully we'll get a value that makes sense. All right, so yeah, when the concentration is very large of HCl, we ignore water. And again, it's because this is a large number, this is a small number, so we can ignore it. But when both of these numbers are small, Can we ignore water's contribution? No, and that sounds familiar, hopefully. That's kind of like all of the approximations we've been making at this time. So we cannot approximate when both of those are small, so let's do it the right way. And unfortunately, this does require the quadratic, where no approximation is allowed. Okay, but I'm gonna show you some tricks on how we ask questions about this. I just want you to feel really smart. Okay, so this is called the common, we're using the common ion effect for solving this. We're doing it for a very, very dilute acid solution. So what we're doing is disrupting Kw, water's equilibrium. So we're going to use an ice table, and we're going to apply it to the Kw expression. So that's Kw, here's Kw, right? Water is self-ionizing into stuff. So when we were calculating the pH of neutral water, we always just started with like a random amount of water. It didn't matter how much. But in this question, it's a little bit different. We start with a random amount of water, but we also want to put the very, very dilute acid in there as well. So that number goes in the initial line of H+. So we're going to just add, we're just going to change up these initial conditions. So H+ is 1 times 10 to the negative 8. All right? So we have a random amount of water times 10 to the negative 8 H+ and 0 hydroxide. That is what's in our container initially. Which way does this reaction have to go? Has to go forward. Why does it have to go forward? There's a 0, yeah. So it's minus x plus x plus x. Cool. All right, so at equilibrium, we have an n minus x of water, but do we care about that? No, because it's a liquid. We have a 1 times 10 to the negative 8 plus x amount of H+, and then we have an x amount of hydroxide. Like all ice tables, what do we do next? Put it into Kw. Shove that into Kw. So we get Kw is 1 times 10 to the negative 8 plus x times x equals 1 times 10 to the negative 14. This requires the full-blown quadratic. We cannot make any approximations, unfortunately. All right? And so we can distribute stuff, right? Distribute that x along stuff. Let's see if I still got it. 1 times 10 to the negative 8 x plus x squared equals 1 times 10 to the negative 14. So to put this into the quadratic formula form, we want to set it all equal to 0 and put the x terms together. So this becomes x squared plus 1 times 10 to the negative 8x minus Kw, 1 times 10 to the negative 14. All right, so that means our A, B, and C terms equal what? A is equal to what? 1. B is equal to negative 8, and then C is equal to negative 1 times 10 to the negative 14. All right, so now you can solve this. Again, you have to, for very, very dilute acid concentrations or base concentrations, you have to do the full-blown quadratic. So when you get this, you calculate that, where is it? X is equal to 9.5 times 10 to the negative 8 molarity. But the molarity of what? OH minus. How did you know that? It's 50-50. The ice table. You have to just see it in the ice table. Yeah, so it's hydroxide concentration. So when I negative log that, that gives me POH. And so the POH of the solution is 7.02. So that makes the pH 6.98. This solution is now acidic. Does that make your brain happy? Yes. Because something was really messed up when it was pH of 8. You put an acid in solution, it needs to be acidic. Now it is acidic when we consider the autoionization of water. But unfortunately, this does require the quadratic. I told you that on exams, we never force you to use the quadratic, that an approximation can always be made. So here is a question that I found from a MCAT prep book. All right, I like to peruse it sometimes to find questions that align with what we're learning about, and this one's straight from the MCAT. Technically does not require the quadratic formula. So it was this. It was, what is the pH of a solution with HCl is 1 times 10 to the negative 8. Here's the thing. 50% of students are just going to negative log that number and say pH is 8, and they're going to move on. But they're not going to think about it. What did you put in water? An acid. So what should the pH be? Acidic. It's not like the laws of physics just cease to exist anymore, all right, when things are really dilute. No, it still follows the same thing. So this question, you technically don't need to do the quadratic. You can just think your way out of it, all right? Because is the pH 8? No, it is not 8, okay? But you know 50% of those future doctors, they're going to put 8, but not you. Not you, because you're always asking yourself, what am I putting into water? What is the pH that I'm measuring? Okay, what other values can we eliminate off of this? 7 point, or so yeah, exactly 7. Why can we eliminate 7? It's not neutral. We put acid in it. It has to be acidic. And what else? 702. And so it has to be C. Okay? You put a tiny, tiny bit of acid in. It needs to be a little bit acidic. A little bit acidic. Okay, and so let's just kind of put it together. Why do we have to consider Kw when HCl concentration is small? It's because when HCl concentration is small, both HCl's contribution and water's contribution, they add up to like give a new number. Both of these numbers are small, so you have to consider both of them. But if I have HCl equals 1 times 10 to the negative 3, we don't need to consider water because this number is really large and this one is really small. So we can just ignore it, right? This one has a pH of 3. You can ignore water. But here's the thing. The ice table is still going to work. If you put 1 times 10 to the negative 3 in this ice table, you're still going to get a pH of 3 at the end. You're still going to get it because you're actually going to, you can make an approximation that says, oh, you know, this number is really big, then plus X is really small. Doesn't that sound familiar? Yeah, and so all of that works out here with the autoionization of water, most important when things are very dilute. Okay, there we go. That's my favorite thing in 1220 because I've prepped you all this way. Okay, I've asked you the question ad nauseum. You know, you put something in water, is it going to be acidic or basic? But then I trick you in that one. So do make sure that your answer matches your intuition. Okay, so other things that we're going to explore in this chapter is the common ion effect. Actually, the example I just showed you is actually also the common ion effect. But really what it is you have more than one, so 2 species in your initial line. That's the big idea. Because in chapter 16, we only ever put one thing in the initial line. It was like, you know, a number and then 2 zeros. But here with the common ion effect, we have 2 things in our initial line and we calculate things. But it's all the same. So if we think about this in a conceptual way, how does this change, adding, you know, something to our equilibrium and disrupting it, how does that change our observations? How does that change the pH? In chapter 15, we just predicted shifts and stuff. We used to like, oh, add product, shift to reactants. But now we can still make shifts, but now we can measure shifts in a different way by measuring pH changes. So let's see if this matches our intuition. Pretend we just have pure water hanging out, self-ionizing with itself at pH 7. And we add H+. Okay, so if we add H+, we're going to do this 2 ways. First, your intuition says, what should happen with the pH if we add H+ to pure water? pH should go down because it's acidic. You add an acid. Perfect. So let's see if this matches our intuition. So right now, we have like, you know, water, random amounts of H+ and OH-. At equilibrium already. We add a product. What does Le Chatelier's principle say happens? The reaction shifts in reverse, right? You add a product, go to reactants. So the arrow I drew also tells us the signs of the change line. We're not going to do an ice table, but tell me, what are the signs under all of these species in our ice table. It's underwater, it's going to be what x? Plus, and then it's minus x, minus x. You're going to consume products and produce more reactants when we add H+. So what's changing here, I'm going to ignore H+ because we're adding some and then it's being consumed, so that's kind of a harder change to grasp. So let's look at hydroxide, how that's changing concentration. I didn't add any hydroxide, but me disrupting this changes hydroxide concentration. So right now, when the solution is neutral, right, hydroxide concentration is 10 to the -7. When I add H+, the reaction shifts to reactants. So how does hydroxide concentration change during this shift? It goes down. Perfect. If the concentration goes down, the molarity gets smaller. How does the value of the POH change? It gets bigger. Yes, gets bigger. So how does the pH change? Goes down. And what does that mean about the solution? It gets more acidic. And does that match with what we guessed at the very beginning? Yes. So that's how the common ion effect works. It matches Le Chatelier, matches our observations. We see all of that. Okay, let's do another one. Let's say we have acetic acid at equilibrium. All right, so we got like HA at equilibrium with H+ and A-, right? Okay, we add sodium acetate to this. So right now this acetic acid's chilling. So we add sodium acetate. What are we adding to the solution? HA or A-? A-. So we're adding A- here. Add. Just think Le Chatelier's principle. So what does Le Chatelier say? Add a product, shift to reactants. Perfect. But let's think about this in chapter 16. You add sodium acetate to water. Sodium acetate's a what? Base. So the solution should become more basic. Yes, this is a base. Our pH should become more basic. Let's see if that happens. So we add A-. Reaction shifts backwards. What are the signs of my minus and plus X? So under acetic acid, HA, it is plus X, minus X, minus X. So how is H+ changing? Because that's related to pH. How is that changing during this shift? H+ concentration is going down, so how does that change pH? Goes up. Yes, and so that is consistent with the solution becoming more basic. And does that match our intuition? You add a base to water, it should become more basic. All right. And so what I've actually created right here is a buffer, right? A buffer is when we have large amounts of acid and its conjugate base present at the same time. That is what a buffer is. All right. So to introduce buffers, I want to remind us, we haven't had this situation yet. In chapter 16, we calculated the pH of just HA. I gave you Ka of HA, you calculated the pH. HA was the only thing that was in that solution. In chapter 16, we also had you calculate the pH of A-, right? The conjugate of a weak acid. So you want to use Kb, but you had to calculate that. That was Kw over Ka, all right? We already did this. That was chapter 16, where it was either only HA or only A-. In chapter 17, we have this new scenario. Well, what if you have both of them? HA and A- in very large quantities at the same time. That is a buffer, right? So this is the definition of a buffer. You need a weak acid and its conjugate base in large quantities. Large quantities, okay, like mole amounts, right? So a weak acid and a conjugate base can be a buffer, but what about a base? What if I start with a base? How could I make a buffer with like ammonia? You have to add its conjugate acid. So that is another buffer system, right? So an acid and its conjugate base, or a base and its conjugate acid, right? So buffers resist pH changes because when you add a strong acid or strong base, what you're doing is actually just converting, neutralizing your base and conjugate to one another, or your acid and its conjugate to one another, and your pH doesn't change that much. So that's why when we drink a soda, the pH of our body doesn't change drastically, all right? Because we have buffers in there to prevent drastic pH changes. And so we use a new equation to solve for buffers, and that is the Henderson-Hasselbalch equation. I hate this equation. And I'll show you why in a minute. But the pH equation is right here. I'm not sure if you're given it on the exams, but I'm going to just tell you that the Henderson-Hasselbalch equation is just the Ka expression with a dress on. You just take the negative log of both sides, and then you get an equation named after you. But that's the Henderson-Hasselbalch equation. And we're going to use that, and that is specifically for buffers. So let's do the exam. Let's make a buffer, and then maybe do one question. And then hopefully you'll feel really, really smart. Okay, so let's make the pH of, what is this, acetic acid? So HA. Okay, that's from chapter 16. Hopefully you can calculate, tell me, what is the pH of this without doing the ice table? How do I set this up? This is HA, a weak acid. It is what? X squared over 0.1 equals Ka, 1.8 times 10 to the negative 5, yes. Right? We only have acetic acid in solution. So this solution should be acidic. So solve for X, you get H plus is equal to something 0.00134 molarity. That's the concentration of H plus, so go ahead and calculate the pH. It's 2.87. Good. Add an acid to water, or add an acid. It should be acidic. Cool. So let's do what we just did before, all right, where, okay, we start with a acid at equilibrium, a weak acid. So here acetic acid is just chilling at, pH 2.8. Now you add sodium acetate to it. Sodium acetate is a what? Base. So how should our pH change? It should go up. It should become more basic, but let's prove it, okay? And this is the common ion effect. So before anything takes place, right? So let me actually do the ice table this time, where, okay, this is HA, here is A minus, the conjugate base. How we're changing this up is now we have 0.1 molarity HA right there. So this is HA. So we have 0.1 molarity HA. So that's the ice table I should have done in the first part, but I didn't. Now we need to figure out, because this is the common ion effect, is what is the concentration of A minus also before equilibrium is reestablished. So using the information in this question, we're going to use this piece we didn't use, 1 mole. So if you put 1 mole in 1 liter, what's the concentration of that conjugate base? 1, yeah. See how I like to make numbers easy? So this is 1 molarity. Again, because it's 1 mole over 1 liter. If the volume was different, you would have to get a different, you actually calculate that concentration. Okay, how much H plus do I have initially? What do you think? 0, perfect. So which way does this reaction have to go? Forward, minus X plus X plus X. So at equilibrium, I have 0.1 minus X, X amount of H plus, 1 plus X of acetate. So this is A minus, H plus, HA. What's the trick with ice tables? The E line goes into K, as always. So our Ka expression is H plus times A minus over HA, all at equilibrium. So that whole equilibrium line goes into the Ka expression. So this equals X times 1 plus X over 0.1 minus X equals Ka, so 1.8 times 10 to the negative 5. Boom, all right. Does that look easy to solve? No, X shows up 3 different places, yeah. So this is not easy to solve. What do you think the approximation we can make is? Do you think X is going to be a big number or a small number? Small. So would it make sense to get rid of the minus X in the denominator? Yeah, because again, X is really small, right? If X is really small, you're not going to change 0.1 that much, so we can get rid of that. Is there something else we can make this easier on us? What about this x? It's the same x, right? You just told me x is really, really small. So in your head, do 1 plus a really small number. Does 1 change? No. So if this is really small, can I also approximate, do that? Yeah. So let's do that. Let's approximate both those things. X is really small, and the number we're adding or subtracting from is really large. That's why we can approximate. So I don't know about you, but I think this approximation is a lot easier. 1.8 times 10 to the 5. Can you do that? Yes, that is quite straightforward. X is equal to something. 1.8 times 10 to the negative 4? Is that it? Negative 6, thank you. See, that's what happens when I try to do stuff in my head. Negative 6 molarity, but it's the concentration of what? Hydrogen, H+, yes, proton. Yes, because we used Ka, and then go ahead and calculate your pH there. All right, so this is a buffer. Also, does this match our intuition? We added the conjugate base, right? You added the conjugate base. Adding a base should make the pH go up. Did the pH go up? Yes, it did. All right, so this is the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation is based on this approximation. So I'll go back to this step where I took the ice table, I set it all equal to K. We had this plus X and minus X in the denominator, all right? So what we want to do is that approximation is you get rid of both of those. So we're making the assumption that the concentration of like HA at equilibrium is actually equal to its initial concentration. That's the approximation we're making, and that's the approximation the Henderson-Hasselbalch equation makes. So what these two people did is they took the Ka expression, they took the approximation, they took the negative log of both sides, rearranged it, and came up with this new equation. This equation, pH equals pKa plus log base over acid, is just the Ka expression where you've taken the negative log of both sides. If you come to office hours, we can prove it, but that's what this is, right? Where the pH of a buffer is equal to, what is pKa? Negative log of Ka, that's exactly what it is. So if I give you Ka, then you can get the pKa. Log base concentration over acid concentration. So these can be in molarities, but they can also be in mole amounts. So if I know how many moles of B I have and moles of A I have in the same solution, I can get that base to acid ratio, right? We can do that because as long as both of them are in the same solution, the base to acid ratio doesn't change in the same volume. So we use this Henderson-Hasselbalch equation when both the base and its conjugate acid are both present in large quantities. So in both of these questions, and we'll do a ton of examples, both the base and the conjugate acid, where's that, HF, they're both present in large quantities, so we can use the Henderson-Hasselbalch equation. All right, so we'll pick up here on Thursday. I would suggest getting a head start on Chapter 16 homework. Doing those calculations will help us in Chapter 17 as well.